Welcome to another GCBASIC demonstration. This is part 2 of the tutorial for the PIC16F175 family. So I'm going to be using a 16F175xx, but this applies to all that family. So what we're going to do now is part 2, sequence some LEDs. Very simple. So please like and subscribe. I'm in it for the like and subscribes. If you want to donate, I'll show you how to do that later on, but like and subscribe is important. So what is the PIC16F175 chip family? It's a high performance PIC. It's got digital and analog peripherals, 10-bit ADCs, pretty standard communication interfaces in terms of serial, that's the UART, I2C and SPI, PMW, and CLCs. I'll show you the CLCs, quite complex, but not too bad, not too hard to use with GCBASIC. Integrated op amps, 4 on board, and it comes in various sizes in terms of 14 through to 44 pin products. I'm using a PIC, a PDIP product. So what we're going to do, as I said, is make 4 LEDs flashing sequence, and this is part of a larger set of tutorials. So what is GCBASIC? I won't show this slide anymore in these tutorials. Open source compiler does PIC AVRs and LGTs. They are LGTs on an AVR clone from China, and it now supports the PIC16F175 chip family, and that's why these tutorials are useful for those coming in to GCBASIC who've selected that chip. They can sort of have the assurance that it's been fully tested, and these tutorials take them through that process in terms of education as well. So I assume that you've installed GCStudio. If you've signed up for updates, you may see an email like this. That's what I saw today. And when I logged in this morning, it automatically updated my system. That's because our development team have updated the toolchain. And when the toolchain gets updated, you may get an email like this. You've installed your programming software and you have that PIC attached, and I'm going to show you my board in a moment. So what we've got is prototype board, powered at 5 volts. You could do it at 3.3, don't really matter. In this case, a programmer and some LEDs and resistors. And I have moved them from port B to port C. So I'm now talking to port C, and I've got 4 LEDs hooked up via suitable resistors to port 0, 1, 2, and 3. I'll show you my board. This is my board. Static picture I took this morning. Let's look at it for real. This is it for real. This is the programmer at the back. This is connected in. I've got 4 jumper leads connected to 4 LEDs sitting over here. And this is where we left it yesterday. And all I've done is connected essentially port C and 0, 1, 2, and 2, and 3 to these 4 LEDs. And for those who've got very good eyes, there's a set of resistors underneath this board here that connect it through. So I can now program it. So what are we going to do? We're going to simply do a bit of logic. We're going to initialize the PIC. We're going to set the value of the first LED. We're going to do a delay, and then we're going to rotate. New command, rotate. And if after a number of rotations, the value of that rotation port is equal to 0, just reset it and go back to where we started. So it's quite simple. Let's have a look. Yeah, that looks really good. And let's get started. So what we're going to see is rotate with a delay. It's going to use the port C register via a constant. We're going to see the rotate command and just some simple logic. So let's get started in here. So I'm just going to press the Windows key, GCStudio, to start GCStudio. Now, it opens up the GCStudio menu. I'm just going to zoom in on that so that we can have a good look at it. So yesterday on the first tutorial we did an open folder and we opened it to this folder here on the left. See if I can mark it for you. There we go, mark the wrong thing. It's here, it's in GCStudio, GCBASIC demos, vendor boards, Great Car Basic demo board, which is that big green board, and these chip range demonstrations. Now, because I've been in there before, it remembers it, so I can simply click on it and it will take me into the IDE. IDE opens up and we see the cow, which is great, sitting there. And that's where if you have an empty IDE, Integrated Development Environment. For those who are following along yesterday, we can look at the files in this folder by pressing Control B or selecting this little Explorer tab at the top left-hand corner. Got lots of files in here, and I'm going to take 040 rotate the LEDs .gcb. Now, when you're in here, you can actually click on that, and it will open it up in the editor. Now you can shut that down by pressing that little Explorer and get rid of it. We're looking in the code. So let's have a walk this code and see what it says in here. Remember, anything in green is a comment. You can review that at leisure. So this two lines here are crucial. The first line, #chip, tells it, the compiler, which chip you're intending to use. An option explicit is really a good practice to ensure that you've defined all your variables. You might think that that's not important. You will learn that it is. Option explicit it tells the compiler to ensure you have defined your variables, and that stops you from making errors in typing mistakes, etc. Little diagram here which we saw in my PowerPoint, which tells me the layout of the board, and I'll keep that updated. Now into the code. So what I'm going to do, I'm going to define a series of constants, a constant that is actually the port. And the port I'm using is lat.c, and lat.c is essentially port C. It's called the latch, and if you write to the latch, it ensures that it's set correctly for you. Now, if you put port C in there, it would still work in GCBASIC, because GCBASIC essentially knows what you're doing, and it says, oh, well, he wanted port C, but I'll change that to lat.c for you. So it does that sort of intelligence. Then, because I've got 4 LEDs on there connected to RC0, RC1, RC2, and RC3, they are constants that are defined within the chip. They're chip names. They're not something that GCBASIC defines. It's actually defined by microchip, and we use those same names because we have configuration files that we have imported as part of the setup process for this particular chip family. RC0, 1, 2, and 3. I'm going to set them auto outputs. Now my LEDs are outputs. So I've got this constant called LED port, and I'm going to set that to a value of 8. And if I do look at that in binary, if I hover on it, if I hover on it, I see the binary 1000, which is in red here for us, look, 100. Essentially, I am going to set the LED port and set the third bit to 1, turn it on. That's my initial value. I tell you what we're going to do. We could stop the program here by saying end. Let's just program it. Let's see what happens. I pressed function key F5. And we can see where we didn't have an LED before, it's actually set that LED on. We go back to our code and we set this to another bit value. Oh, we could do this, look. We can say, all right, let's just play with binary numbers for a moment, and I program it, and I'm just shifting it along. I'm saying now set the second bit. We can see that the LEDs come on. Let me make sure that you can see that camera. Just unlock it for us. It was locked already. I'm just going to make that bit bigger for you. There we go. Just lock everything down so that I don't make a mistake. So we can see that that's back on that third LED. Now, if I just revert my code by pressing Control Z, I can put it back to where we were, press function key F5, and it will then just set bit 3 or set the port to 8. Great. Let's get rid of that end, move on. So I've got a do loop in here. I'll get rid of that. A do loop, and this is the do loop. You can see it here. I can collapse the do loop, and it will do everything forever within that do loop. It says wait for 1 second. We saw that yesterday in the first tutorial. And I say rotate the LED port to the right. So what it's going to do, it's going to take that number, the value of that port, which is referenced via the constant, and it's going to shift it to the right. Effectively divide by 2. It's going to take the contents and shift it, a binary shift. If the LED port is here 0, it means that nothing is set. It will reset the LED port back to 8. And what we've introduced here is the if statement. If, then, end if. So it's a standard type construct. So if the port is equal to 0, then set the LED to 8. Program it by pushing function key F5. We now have 4 LEDs rotating. The delay period, let me just shut that window down. The delay period is set by 1 second, and that is calculated when you specify the chip frequency. But we didn't set the chip frequency, did we? Well, we did. Up here in the chip line here, if you look at the syntax for that, you can put a number behind here, and that number here, like 32, will set the frequency. But there's a default, and that default is shown to you when you compile. So let's look at that. I press function key F6. I pressed F6 because I just wanted to compile it. If we look in here, it says chip resource usage, 64 words, no RAM, which is true, we haven't used any RAM. Then it says the compiler has chosen for you the fastest speed of the internal oscillator, which is 32 megahertz. Do you know what? That's correct. So how do I change that? Well, if I want to change that to 1 megahertz, I'll press function key F6 and we'll see what happens. It now says it's chosen a 1 megahertz internal oscillator. Now, if I choose a value that is not inside of and if you notice, actually, if I program that, the wait command is the same because it's recalculated the delay period required for a 1 second delay. It does that fully automatically. I think it shouldn't. Is 31K valid? Let's have a look. Let's have a look at what 31K says. It says here that it's selected the 31K internal oscillator. So you can use many of the different internal oscillators. The moment that it doesn't recognize the value, you have to specify a config line. Let's just see what happens when we program it there with the 31K. If you look up the help, and it still works exactly the same, even though the chip is on low power because it's running at 31K, the calculations of 1 second has been optimized for you automatically. And there may be reasons why that isn't suitable for your use case, but generally that is quite useful. So if we look up the help on hash chip, I'll type it in here, into the help, hash chip, first entry, it's got some help for us. And it says that help is the following. Chip, the model, the frequency, or a numeric constant. And that numeric constant, I just put one in. If you look at the help here, you can put in 31k, 500k, 250k, 125k, or a number, or a bit of a maths. Look, don't know why you do that, but you can. Look, quite flexible. But generally, the general rule would be to put nothing in there and just leave it at 31k. And we'll go back to that. I'll just go back to my desktop. 31k set now, and we're running. That's all I wanted to show you on this video. So now, in the next video, we're going to move up to using the ADC. We're going to set the LEDs to represent the value of the ADC. So as I play with the ADC value, it's going to set the LEDs. Quite exciting. Could be a delay from the ADC, could be something else. We'll see. Enjoy.